Today we're talking about sets. Be careful with sets because they start easy, but then they stop being easy. So you've got to be. I'll start with some definitions, and you think, "Oh, this is obvious," and then suddenly you'll find that it isn't. A set is a collection of things, and it can be anything. Sets are amazingly versatile, and they are used for working out complex logic. A lot of the stuff that excuse me, a lot of the stuff that we'll be doing isn't complex logic, but we're setting the ground for complex logic. So what can it be? It can be real, like bananas, cars, people, shoes, mountains, you know, whatever you want. Or it can be virtual, like the set of integers, the set of real numbers, the set of prime numbers. So it doesn't have to be a real thing. It can be a mixture of real or virtual. Sort of anything can be a set. And in fact, nothing can be a set. That's to say, you can have a set with nothing in it. So we write a set normally with a capital letter, so A, and we denote it being a set with curly brackets, which I always find difficult to write. So A is, this curly bracket means the set of, and I can say it's A, B, C, and D, okay? Or I could say A is the set of, you know, Fred, Susan, Mohammed, and Nikita. Okay, that's a set of 4 people. So, just going over the documentation, we tend to use capital letters for sets and lowercase letters for the elements of sets, and the curly brackets at the beginning and the curly brackets at the end define the set. Okay, so that's just what a set is. We have something called U, which is the universal set, which is everything, T-H-I-N-G, in the problem domain. So you define what the problem domain is, and therefore you define the universal set. But if I'm doing a problem that includes all prime numbers, for example, then U would be the set of all prime numbers. Okay, I could also define the set of all real numbers, or all integer numbers, or, you know, whatever you want to do, but the universal set is everything in the problem domain. Right, sometimes we have a set that is infinite, and obviously if you needed to write all of the elements, it would take you an infinite amount of time. So let's say A is the numbers that go from 1 to 100. So what we could say is that A is equal to the set, and then you put the bar character, and then say n is greater than or equal to 1 and less than or equal to 100. Okay, so what we're saying here is A is the set of numbers n, where n is greater than or equal to 1 and n is less than or equal to 100. And this thing here, which defines the set, is called a predicate. What we've got here is a description of what this thing is here, and the thing that is on the right hand side of this bar character, which is next to the Z character on your keyboard if you're sitting in front of a keyboard, is called a predicate. Okay, and you can put anything you want in the predicate to define what is actually going on in the set. And just now I've had the question, we've got we have a couple of symbols. For instance, we've got that fancy letter N, which is the set of not integers, what are they called? Natural numbers. And then the set of integers is actually normally a Z, like that, which is the set of integers. And the real numbers is the set of real numbers. Okay, and for the sorts of things that we're likely to be doing, we're probably just using numbers or letters or something to represent sets until we get the algebra sorted out, and then we'll move into questions that actually use meaningful objects, meaningful elements in the set. Okay, right, I'll blast along. So now we've got a symbol which is like this. It's like a sort of curve E, and that means is a member of. So we can say that 3 is a member of the set of natural numbers. So that's meant to be a fancy n. Okay, so how you'd read this is 3 is a member of the set of natural numbers. Okay, and that's what that means. And then we have a similar symbol which is like that, but with a line through it. And I bet you can't guess what that means. Obviously it is not a member of the set of natural numbers. Okay, Euler, you know, the mathematician Euler, he started with having diagrams where he put a sort of a loop around things that were in a group. So he just drew a border around things that were grouped together. And John Van, who is an English mathematician, he improved that. So he started with putting numbers like this. So if we've got 4, 2, 8 and 6, and we've got another set which is 3, 2, 7 and 5 in another set. Okay, so we can say that this is set A and this is set B. What Van did, he said, well look, we've got an element here which is in both sets, so we can redraw this like this. So we can have A like that, B like that, and in the middle we put 2, and then we've got 3, 5 and 7, and on this one we've got 4, 6 and 8, and 2, as you can see, is in both sets. So that was Van's improvement on Euler's set notation. Euler just put a line around a group. Van realized that you can actually intersect sets in the way that I've done there. And obviously you can intersect more than 2 sets. You can intersect as many as you want. Also, we tend to draw these as circles, but there's no reason why they need to be ellipses more than circles. There's no reason why they need to be ellipses. They can be any shape you want, and some sets use star-shaped. Right, just to answer Robin's question, the mathematician who designed these, and he's called John Venn. Some people call him John Venn. I went to university with his granddaughter, and she was actually called Jean Van. So her name was like this, Jean Venn, and she pronounced her name Jean Van. So I suppose that's why I call them Van diagrams, but you call them what you want. It's entirely up to you, because of course you didn't go to university with her. Okay, so looking at the diagram that I've put there, figure 13.2, and obviously this is out of baseline, how many different areas are there on that graph? We've got some bids there. Right, well, let's just imagine we've got A, so I'm calling this part A. Oops, so the pen. I'm calling this set here A and this set here B. So we've got A, all of the elements in A. So we've got A, which is equal to 2, 4, 6 and 8. And let's do the next easy one, which is B, which is equal to 2, 3, 5 and 7. I should separate these by commas, and for the record, baseline needs you to separate them by commas, so it knows that you're talking about 2 and 3, not 23. Okay, and then we've got the elements that are in A and B. So A, and then there's this thing here, which I'll explain in a minute. So that's all of the elements that are in A and in B. Well, obviously that's the 2 that we've got there. That's the 2 we've got there. So that's the set that just includes 2. Okay, the numbers are going up now, aren't they? So we've got the elements that are in A and not in B. Then we've got the ones that are in A and they're in B as well. So that is equal to 2, 3, 4, 5, 6, 7 and 8. Comma, 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 comma. Okay, so that's everything that's in A and in B. Right, and then we've got this one here, which is called not A, and that's the elements that aren't in A. So that's the group called 3, 5 and 7. Okay. I'm going to make this a bit smaller because I want to keep the whole thing on the screen so we can see what we're getting to. Right, so that's the elements that aren't in A, and then of course I'm going to get the elements that aren't in B. So the thing, oh, have I missed the elements that aren't in A? That's right, and the elements that aren't in B are obviously going to be 4, 6 and 8. Okay, and then what else have I got? I've got this element here, haven't I? So A intersect B, and then I've got what's not in there. Let's just think what I mean by that. So look here, I've got A, this is called the intersection. As I say, I'll describe that in a minute, but this is the A intersected with B, which is the stuff that's in A and it's in B, so that's that element there. So this is saying all of the things that are not in that set, which means that we're talking about 3, 4, 5, 6, 7 and 8, aren't we? So that's these elements and these elements. Okay, so that's 3, 4, 5, 6, 7 and 8. Right, so let's take those off there, and so that's 1, 2, 3, 4, 5, 6 and 7. Okay, now there's just one more, which is 8, and that's going to be A intersect B inverted. So here we've got A intersect B, and that's all of the numbers 2, 3, 4, 5, 6, 7 and 8. So this one here is actually going to be the null set. Okay, so that's the one with nothing in it. So weirdly, we take this diagram and we thought there aren't so many areas there. Suddenly we find we've got 8 different areas, all of which could be meaningful. So if you were trying to find out how many people in a particular region who pay their council tax have an electric vehicle and therefore use power, you would quite easily be able to interrogate a database using this sort of logic to say these are the different categories that I'm looking for, and the sort of logic that we're using here is what you'd use to do that. So very much used in subjects like AI is all of this. Right, so I've used a couple of things, a couple of expressions there which I need to explain. So we've got this character which is called cap, and this means the intersect two sets. And the reason I say 2 sets, it could be more than 2 sets, but you take 2 sets at a time. So that's elements in A and in B. So intersect is the stuff that's in both sets. Okay, and then we've got the union is everything in A and in B. Then we've got we have a set symbol, and we can either have a dash, a -1, a T, Is there anything else that we use? Oh yes, and we could also write it like this. We can do a set with a bar across the top, or say the letter A with a bar across, and that's the inverse. So if you've got a set A, a line across the top, not A, means that anything that's not in A, and the set with a line across the top, you could just use a single quote or a -1 or a T. Any of those mean an inverse. Different groups of people use different symbols. Something like this, which is called the null set, which is a set, of course, with nothing in it. So let me do an example. Okay, so we've got A, B, and C, and they want us to draw the Venn diagrams of those things. So we've got A union B. So obviously A union B is equal to, so we've got A, B, C, D, E, F. That's fairly straightforward. A, C, D, F, and H. So the A union B is going to be A, B, C, D, E, F. A, B, C, D, E, F, and we've also got H. So the union of those two, that answer there. And then we've got A intersect B, so A intersect B, that is equal to, now this is just things that are in A's and B's. So now we're looking at what's in A and what's in B. So we've got A, and we've got A there. That wasn't very good. Let's do it again. So we've got A and A. We've got C and C. We've got D and D, and we've got F and F. Okay, so that means we've got A, C, D, and F. D and F. Okay, and then we can start getting more complicated by bundling up different groups here. Okay, section A, sorry, I've misunderstood that. This is B here, and this is C here, but A says draw a Venn diagram of all this stuff. So let's do that to start with. So we're going to have three loops, aren't we? So we've got a loop for A, a loop for B, and a loop for C. So I'm going to call this A, this B, and this C. Okay, now let's just see what we've got. Let's try and find everything that's in everywhere. So we've got F, which is in all of the sets, isn't it? So F is obviously going to be in there. I've got H. I've got X and Y here, which is only in C. So I've got an X and a Y there. Okay, I've now got E that is in A and C. So A and C has got an E in it. Right, so that's taken care of C, which is the smallest set. I'm now going to do B because that's the next smallest set. I've got A and C and D, which are all in A. So I've got a bit of a squeeze. A and C and D. I've got F, but that's in both. H is only in B. So then left for A, we've got A, B, C, D, E, F. Okay, I think that's the answer to that. So let me just check. In A, I've got A, B, C, D, E, F. A, B, C, D, E, F. In B, I've got A, C, D, F, H. A, C, D, F, H. Yeah, that's okay. And then in C, I can see that I've got E, F, and X and Y. So that's the answer to question A. Draw a Venn diagram of the whole thing. It's a scruffy Venn diagram, I grant you, but it is a Venn diagram. Okay, then for question D, how you would approach a question like this is you'd start by taking B union C. So what we've got then is B union C is equal to A, C, D, E, F, X, Y. So that's A, C, D, E, F, X, Y. Okay. A, C, D, E, F, X, Y. And then we're going to take the intersection with that with A. So then A intersect B union C is equal to, So we'll have A and C and D and E and F. So that's all of A except for B, isn't it? All of set A apart from B. So we've got A, C, D, E, F. So the answer to that one then will be A, C, D, E, F. A, C, D, E, F. Okay, and obviously the part E, we'd carry on with that in the same way. Sets and supersets. We've got a set. I'll use the sets that we've got here. A is equal to A, B, C, D, E, F. If I had a set A, B, C, let's call it a set called X, that was A, B, D, and this is, okay, so that's A and X. And also let's have another set Y, and that's equal to A, B, C, D, E, and F. X is a subset of A. Why? Because it has all of the elements that are in A in X. So we say that X is a subset of A, which means X is a subset of A. Okay, because everything in X also is in A. We can also say that Y is a subset of A. So Y is a subset of A, because everything in Y is in A, and in exactly the same way we could say that A is a subset of Y, because everything in A is also in Y. But you can see there's a difference between X and Y, can't you? And because everything in X is in A, but there are some things in A that aren't in X, we can actually say that X is a proper subset of A, and that has this symbol. So X is a proper subset of A. Okay, so let's just go over that again. This symbol without the underline, X cannot be equal to A, so in that case we're saying that it's a subset or it's equal to. That's what this symbol means. But if it can never be equal to, then it's a proper subset. It's not just a subset. Can you also say that X is a subset of Y? Yes, you can do. That's also true, because Y is exactly the same as A. So what we could write here is, so we could say that Y is equal to A. So A is a subset of Y, Y is a subset of A, and X is a subset of both of them. But in fact, X is a proper subset of both of them, because there are elements in Y and A that are not in X. And if we imagine, let's do it in red, if we imagine taking F out of Y, then Y becomes a proper subset of A, and X is still a subset of Y and a subset of A, but Y is now a proper subset of A because it's not equal to it. Okay, power set. So the power set is the set of all subsets. Okay, the power set, if I've got a set which is, let's say A is equal to A, B and C, how many subsets can you identify for A? B and C. If we've got the set A containing A, B and C, the number of subsets we've got are A, B and C, A, B, A, C, B, C, so that's all of the 2's. Then we've got A, B, C, so that's all the 1's, and then we've got a 0. So we've got 1, 2, 3, 4, 5, 6, 7, 8. 8 is equal to 2 to the 2 cubed. We've got 1, 2, 3 elements, so the number of subsets is equal to 2 to the power of number of elements And because number of elements takes a long time to write, mathematicians, who like to use fancy words, call that the cardinality. Okay, you might have heard of the cardinal numbers, which are actually the same as the natural numbers. So the cardinal numbers are 0, 1, 2, 3, 4, 5, 6, 7 and so on. So the cardinality is the number of different elements that are in a set. And so if I ask you, and I will, how many elements are in the power set, you just count these up, 1, 2, 3 in this case. 2 to the 3 is 8, and that's how many subsets. Now, let me do set difference. If we've got a set, elements can only be in a set once. They're either there or they're not there. And so if I've got a set A, which is A, B, C, and D, and I have a set B, which is equal to B and D, A minus B, that's the difference of those two sets. So what you do here is you take away every element that is in both sets. So the B is there, and the B is there, and the D is there, and the D is there. So what gets left is the A and the C. So A minus B is equal to A comma C. Okay, what about B minus A? So we do exactly the same as we did before. So we're taking everything in B that's also in A. So we're going to take away the B and we take away the D. Now A is not in B, so clearly we can't take it away. C is not in B, so we can't take that away either. So B minus A is going to leave us with a null set. Okay, so because we can't take it away. So the next thing I want to look at is the Cartesian product. Good old Descartes. So let's imagine I've got A is equal to red, green and blue, and B is equal to 2, 4 and 6. The Cartesian product, so A times B, so we've got R and 2, R and 4, and R and 6, comma, then we've got G and 2, G and 4, and G and 6, and we've got RGB and 2, and B and 4, and B and 6. Close that bracket and then close that bracket. All the green ones, I've got all the blue ones, and I've got all the red ones. And if you count the number of lines on there, it's 9. If you look at this, I've got 3 rows of 3, which is also 9. So that's the Cartesian product. And I'm going to stop sharing my screen and I'll stop the recording. I can do that whilst we're waiting.